Okay, next we're going to extend the kind of analysis that we did when we introduced permutations in the fifth lecture and look at permutations as sets of cycles with restrictions on the cycle length. Recall that we studied this when looking at introducing analytic combinatorics with the following kind of construction. A permutation is a set of cycles. Then from the symbolic transfer theorem for labeled objects, that means that the generating function satisfies for set its exponential, for cycle its natural log. So P of z equals e to the log of 1 over 1 minus z, which is 1 over 1 minus z. So therefore the counting sequence is n factorial coefficient z n, that is, which is n factorial. And if you want to extend that to same analysis to count the number of derangements, that's the permutations with no singleton cycles, then we just restrict the length of the cycle to be bigger than 1, which corresponds to leaving off the z in natural log of 1 over 1 minus z. So natural log of 1 over 1 minus z minus z is z squared over 2 plus z and so forth. Or another way to look at it is just natural log of 1 over 1 minus z minus z. And then that's e to the minus z over 1 minus z. So coefficient of z to the n that is a convolution, which is minus 1 to the k over k factorial, which is asymptotic to 1 over e. And then we did the generalized derangements if we restrict to no short cycles of length less than or equal to parameter m. It's just a straight generalization of the argument for derangements, where now it's e, and then we start at z the n plus 1 over n plus 1, or that's log 1 minus z minus all the ones less than or equal to m, which is e to the minus z minus and so forth over 1 minus z. And then we showed an analytic transfer theorem that tells us that the asymptotics of that is n factorial over e to the h of m. So that's a review of what we talked about in terms of permutations with cycle length restrictions when introducing analytic combinatorics. And now we'll look at another problem of that flavor, and that's involutions. An involution is a permutation where all the cycles have to be short. So, and they either have to be a length 1 or 2 in an involution. So out of the 24 permutations of length 4, only 10 of them have cycles of length, all of length 1 or 2. The others have either one cycle of length 3 or one cycle of length 4. Similarly, there are only 4 of the permutations of size 3 that don't have any 3 cycles and so forth. So the question we're going to want to take a look at is how many involutions there are. Involutions are actually interesting combinatorial objects with lots of applications. One way to see it is to think again about inverses. Remember, a permutation is a mapping. If we look at the permutation as a mapping of the numbers 1 through n to itself, then the inverse is the inverse of that mapping. So if we think of students in rooms and sort by room and flip the rows, we get the inverse. What's the inverse of an involution? If you take an involution and compute the inverse by, again, sorting by the bottom, sorting the columns so that they're ordered by the bottom row and then flipping, you see immediately that you get back the involution. So what's the inverse of an involution? It's itself. And if you think about the cycle representation, taking the mapping and the cycle representation is just moving one step in the cycle. So if you move one step, if you have a 2 cycle, you move one step and then another step, you get back to where you were. If you have a 1 cycle, you just stay where you were. So always with 2 steps, you're going to get back to the same place. So that's why involutions are significant. In the significance of, so in the lattice representation, the 1 cycles correspond to elements that are on the diagonal, and then the 2 cycles have to be symmetric. 1 goes to 9, 9 goes to 1. And if you transpose it, you get the same thing back. So an involution's its own inverse. And you see that from the lattice representation immediately. And in terms of applications, there's the idea of a reciprocal cipher. So if you use an involution, then what you can do is encrypt and decrypt with the same machine. And actually a famous example of that is the Enigma machine that was used by the Germans in World War II. One of its components was an involution. So the idea is you have our letters from A to Z and minus for blank again. If the permutation that we use to encrypt is an involution, then we don't need to compute the inverse. The involution is its own inverse. So we don't need a separate table to decrypt. If we have our plain text, and then we get the ciphertext, A goes to D and so forth, then to decrypt, we use the same involution or permutation, which is an involution. And that same thing says D goes to A and K goes to T and so forth. So involution is a permutation that its own inverse. And again, it's still susceptible to the character frequency attack, but it's proven useful as a component in a cipher machine because it can greatly multiply the number of possibilities that an eavesdropper has to consider, and that's how it was used in the Enigma. So, for example, if you want to know how many different Enigma settings you have to find, then you have to know something about enumerating involutions. And there's the very famous story about the cryptanalysis of the Enigma involving Alan Turing and so forth. And if you don't know that story, it's definitely worthwhile to look it up and read about it. So as a warm-up, let's take a look at the number of permutations that are composed entirely of 2 cycles. So there's only one permutation size 2 that's all 2 cycles. There's 3 different ones of size 3 that are all 2 cycles and so forth. And actually an example of this is called ROT13. So it's the world's weakest crypto system where we just take the letters and rotate them 13 positions. So A goes to N goes to A, B goes to O goes to B, and so forth. And you can read about this one on the web. It's a hacker's delight because anyone can encode or decode, and people get so they can read in this and so forth. So it's a very light crypto system that hackers use to just lightly to put stuff out on the web that maybe is inappropriate content, but you have to be at least able to decrypt in this way, and nobody get offended if they ran across it accidentally. Again, since it's 2 cycles, it's a reciprocal cipher, so you use the same table to decrypt and encrypt. So how many permutations or controls entirely of 2 cycles? Well, a permutation, we'll call it R, is it's just a set of 2 cycles. 2 cycles is e to the z squared over 2, so the equation is e to the z squared over 2. And so all we want is the coefficient of n factorial times the coefficient of z to the n in that. So that's going to be z squared over 2. So we got the z squared, so it's n over 2 factorial, and that's the equation. And we can do the asymptotics from Stirling's approximation to get the number of 2 cycles. So very simple and straightforward with basic analytic combinatorics and asymptotics. But what about involutions? Well, the construction is pretty similar. It's a set of 1 cycle starred with a set of 2 cycles. So they're just permutations where all the cycles are of length 1 or 2. So that immediately goes to e to the z plus z squared over 2. So cycle 1z, cycle 2z, and then a set of those is e to the z plus z squared over 2. The first one's e to z, second one's e to z squared over 2. So now we want to extract the coefficients. So what's n factorial coefficients of z to the n in that function? Well, that gets to be a discrete sum that is maybe not so easy to analyze. N factorial over k factorial 2 to the k n minus 2k factorial. So it's a convolution of a term like the one that we had for just 2 cycles and then 1 over n factorial. And that's easy to verify. So the asymptotics of that is a bit more complicated. It's got a square root of 2 fourth root of e in it, and it's definitely a intricate looking function. And that's available from the Laplace method for sums. Remember the Laplace method, we isolate where the most weight of the sum is, and then estimate with an integral there, and also bound the tails and so forth. And that's done in Knuth volume 3. Or later on in part 2, we'll see how to, with complex asymptotics, directly get that answer out. So with analytic combinatorics, we can get directly to results like that. Although the asymptotics of that is definitely not trivial. And then if we're going to generalize, how about no big cycles where we parameterize the cycle length by m, same way as we did for derangements. So now the construction is it's a set of 1 cycle, start with a set of 2 cycles and so forth up to a set of m cycles, e to the z squared plus z squared over 2 plus out to z to the m over m. That's direct from the symbolic method. The coefficient asymptotics of that one is one of the most difficult derivations in our analytic combinatorics book. But we can know the asymptotics of that through analytic combinatorics. As an example, now for some applications you might not need to actually work out the full asymptotics, and just as an example, I want to show an exercise. So this is the generating function for the number of permutations that have no cycles of length bigger than 5. So let's say we have permutations of length 10. We want to know how many of those have no cycles of length bigger than 5. So the answer to that question is coefficient of z to the 10 in that function. So that's a very specific question, and it's worthwhile looking at a calculation like that to get some facility for types of problems that sometimes arise. So if we write the generating function in, say, the other form, the alternate form, it's log of 1 over 1 minus z minus then the bigger terms. So that's equivalent. Log of 1 over 1 minus z is the sum of z to the k over k, and if we subtract off the ones bigger than 6, then we get the ones less than or equal to 5. And now with that, we can take e to log 1 over minus z is just 1 over 1 minus z, and then we have the other terms multiplied out. Now the key idea here is that each one of those terms, if we use Taylor's theorem to expand them, we only need to keep the first term. E to the minus z6 over 6 is 1 minus z6 over 6 plus z 12th over 2 factorial times 12, but we don't need the next term because z to the 12th, and we only are interested in z to the 10th. So anything that z to the 12th multiplies by is going to be bigger than z to the 10th, and we don't even need to carry that term. So this is exactly an equality. We just keep the ones that could possibly contribute to the coefficient of z to the 10th. So now the exponentials are gone, and we have this list of polynomials. But if you do the same thing with the 1 over 1 minus z, then we only need to keep the first 10 terms of that one. And then for each one of these, if you cross multiply each one of these, really you only need to keep the one where you picked like z to the 8th over 8th, and it multiplies by 1 in all the other terms. So that's the z to the 8th over 8th. If it multiplies any one of those others, it's going to get something bigger than z to the 10th and can't contribute coefficient of z to the 10th. So now we just have product of two terms, and coefficient of z to the 10th is easy in that because the cross multiply, there's one contribution from each one. It's just 1 minus 1/6 minus 1/7 and so forth. So the minus 1/6 comes from z to the 6 over 6 times z to the 4th, and z to the 1/7 is z to the 7th over 7 times z cubed, and so forth. So if you look at that derivation, you pretty much convince yourself, you can easily convince yourself that that's an effective way to calculate a coefficient like that for a particular problem. As an application, we're going to consider a problem known as the 100 prisoners problem. This actually was a Google interview question for a while. So the idea is you have it's a story where you have 100 prisoners, each have a unique identity card. So the prisoners are numbered from 1 to 100, and they each have a card. Now they've been sentenced to death because they're on the wrong side of a civil war or whatever, but they're given a last chance. And so the last chance is that the ID cards are all collected in this cabinet that has 100 numbered drawers. Cards are collected and shuffled, put in random order, and then they're put in the drawers, one card per drawer. So now that's the setup. And now the prisoners, one at a time, are allowed to go into the room that has the cabinet and open a drawer, look at a card, and then close the drawer. And they get to do that for at most 50 drawers. So each prisoner can look at 50 drawers, but not all of them. And so then when the prisoner comes out, they have to announce whether what drawer their number is in. And if all of them find their own number, then they won't be executed. But they have to all find their own number. If any one of them doesn't, then they're all executed. If one prisoner can't find the number, they're all executed. So now one of the prisoners is a mathematician, prisoner A, and he says, well, this is hopeless. We're all going to die because we can each only open 50 drawers and they're randomly ordered. So that means that we each have only a chance of 1/2 of finding our number, and there's 100 of us. So the chance that we'd all find our number is 2 to the minus 100th. And that is an exceedingly, unbelievably small number. We have no chance. In fact, it won't take too long before somebody can't find their own number. But there's another prisoner who knows some analytic combinatorics, and he said, I think I have an idea. I know a strategy where at least we have a 30% chance of success. So that's the Google interview question is, what's the strategy? So really what prisoner A was saying was that his strategy was going to be pick drawers at random. And obviously that's not the best strategy. So what's prisoner B's strategy? Well, from the context, maybe many of you have figured it out. So the strategy is that each prisoner should follow the cycle. That is, each prisoner should, he knows what his number is, say it's number 5, so he should open the drawer that has number 5, and then use that number to decide what drawer to open next, and then just keep going. Now, he's going to continue until he finds the drawer that contains his own ID. And so that's going to be the strategy. Well, he has to stop if he gets to 50 drawers. So if you think about that, when does the strategy succeed and when does it fail? Well, it's going to succeed if the permutation that represents the cards of the drawers has no long cycles, no cycles of length greater than 50. So what's the chance that a random permutation has no cycles of length greater than 50? Well, it's the coefficient of z to the 100th in e to the z plus z over 2 plus so forth z over 50. And that's just a slight generalization of the little exercise that we just did to see that that coefficient is going to be 1 minus 100th harmonic number minus the 50th, which is about 1 over log 2, 0.31. That's a solution to the 100 prisoners problem and an application of study of the cycle structure of permutations.